So in Physics 1, we spent a lot of time talking about motion. But most of the time when we talked about motion, we talked about things going in some direction happening once. So remember we talked about position. We represented often as x, y, or z, but we'll stick with x for now. We talked about velocity. We talked about acceleration. We talked about all of these with respect to time. And we also talked a little bit about angular motion. And so we talked about circles. And remember, anytime we were talking about circles, we were talking about the fact that there are 2 pi radians in any given circle. So what we're going to start talking about now is not just this one and done kind of motion, but we're going to talk about oscillations. So periodic motions, things that happen again and again and again, the same motion over and over and over again. So let's take a second to describe an oscillator. First of all, when we're dealing with an oscillator, we're talking about something that takes place about an equilibrium position. So, in other words, what I might have is a pendulum, for instance. So with my pendulum, originally, I have some mass hanging from a string, let's say. And if I don't touch it, it just sits there. But if I put energy into the system, if I pull the pendulum back, I'm holding it. I have some potential energy that I've added to the system. I've raised the height of it, if you will. What happens when I release the pendulum? Well, it starts to speed up, and it passes through this equilibrium position. Now, when it's going through this equilibrium position, think about its position, its speed, its acceleration. So what is my, as soon as I release, this is the place where I have the most energy. It's also the place where I'm going to experience the greatest acceleration. Now, when we're talking about oscillators, we're often talking about something called a restoring force. And the idea is the force of gravity is going to pull this pendulum, this bob, back to where it was in equilibrium between the tension and the force due to gravity. So we want to accelerate to this point here. And so in the center, I'm at this point where I'm going the fastest. So I have a maximum velocity in the center here. But since I'm going the fastest and I have some momentum at this point, do I just pull back and the pendulum comes and stops right in the middle, right back at equilibrium? It doesn't because of momentum. So we then have this continuing motion as the pendulum swings further through. Now, assuming I could actually draw symmetric situations, can I ever have more energy in any point of this system than I did when I started? No, conservation of energy says that whatever energy I start with is the energy that I maintain throughout the system, or throughout the motion. So if I start with no kinetic energy, so kinetic energy is 0, my potential energy due to gravity is at a max here. So that's as high up as I pull it. What is my potential energy due to gravity here? Well, I'm actually at a minimum but my kinetic energy here is at a maximum because I'm going at my greatest velocity. So my momentum carries me through. And then when I get back up here, can I ever have a greater, when I get to the point where I stop, let me clarify that. I get to the point where, again, my kinetic energy is equal to 0. Is my potential energy due to gravity here ever going to be greater than my potential energy due to gravity here? No. So in other words, this is still my potential energy due to gravity, and it's the same as it was before. So in other words, I start at some height, I end at an opposite height, if you will, but it's still the same, it's symmetrical. And then when we release, we see the same thing happen again. We go through the center, we're at a maximum velocity, then we come up here to a minimum velocity, a maximum energy. And I should also point out, consider the acceleration in terms of the force. If my net force right here is 0, we say this is my equilibrium position. That's where we started. So here, my net force is 0. What does that mean about my acceleration as I move through this point where my net force is 0? Well, remember, Newton says that force equals mass times acceleration. So that means my acceleration is 0 at that point. So I know I have a maximum velocity, I have a 0-point acceleration. Up here, this is where my force is at a maximum. So remember, we say, F equals m times g, but the idea is at this point, my acceleration is at a maximum. And then my acceleration drops off, but my momentum picks up. My momentum carries me through to this point, back to this place where when I pause at the top, that's the place where my acceleration, again, is at a maximum. So hopefully this is a basic system that you're already kind of familiar with, and we're just kind of defining some things to start with. But when we're talking about an oscillator, the first thing to note is that we're always oscillating about some equilibrium position. The next thing to pay attention to is the fact that an oscillator is periodic. So the motion is periodic. And what we mean by periodic is that it happens, it repeats at regular time intervals. Okay, so it's not that one swing happens faster than any other swing. It's always at the same rate. We have the same rate of change of motion. And when we're talking about periodic motion, there's a couple of terms that we need to define. One would be the period, and the period is the time measured in seconds for one full cycle. Now, in the case of our pendulum, one full cycle is not from here to here. One full cycle is from a given position back to that same position with the same motion. So if I start at my initial drop point, one period is the time it takes to come back to that initial drop point. Now here's a question for you. If I look at my equilibrium position, let's say I go through equilibrium and up, and then back through equilibrium, is that one period, the time it takes to pass through equilibrium twice? It's not, because in this case, as I swing through, I'm swinging to one side, but as I come back the other direction, the motion is in the opposite direction. I'm not actually at the same part in the cycle. Even though I'm at the same position, I'm not at the same point in the cycle. So it's important to recognize that the period is the time it takes for a full cycle. In other words, for it to look like, for it to look exactly like it has at a previous point. And while we're talking about period, we can also talk about the word frequency. So the beauty is, if you know period, you know frequency. If you know frequency, you know period. But it's important to distinguish the difference between the two. So period is the time it takes for one full cycle. Period is the number of oscillations or cycles per given amount of time, usually per second. So for period, I say that I represent it with the letter T. You can think of it as time being T. And it has units of seconds. For frequency, we represent that in our equations with the letter F. And it has units of, so cycles per second, so 1 over seconds, or hertz. Now, it may seem a little confusing sometimes that we drop cycle as an actual unit. Sometimes it may be useful to include, just for your own sake, that the period is the time per cycle, so seconds per cycle, or the frequency is cycles per second. It's kind of like radians when we're dealing with angular motions. A lot of time we just drop the unit of radians. So just kind of be aware of that underlying use of the unit. So let's talk about a couple of different types of oscillations. An oscillation is anything that is periodic and anything that oscillates about an equilibrium. So we have our pendulum example here, and I'm gonna draw a few, we'll call them waveforms. So the first one we can say looks like this. So I'll even let that be my equilibrium point. I might have another wave that looks like this. And I can give it some equilibrium point here. Then, of course, there's a sine wave. And just for kicks and giggles, I'm going to draw a second sine wave. And I'm going to draw a funky wave. So we'll say that this is our equilibrium position. Okay, so let's kind of compare and contrast these waves here, these oscillations. They all go back and forth across some equilibrium position. And so they all have a period. So I can talk about the period being from peak to peak, or I can talk about the period being from trough to trough, or I can talk about the period being from where I cross the line at a downward position to here. Is that a period? No, because like we said, it has to be going it has to not only be in the same position, but it also has to be going in the same direction. So here to here is truly a period. And we can do the same thing with our other types of waves. So notice that from the way I've drawn this one, I've actually only drawn one period here. So just understand that I can have waves of similar amplitude. That's another term we need to be familiar with. Amplitude is my distance from equilibrium. So it's my distance from my equilibrium position. And we represent it with the letter A. And since it's a distance, it usually has units of meters or centimeters or some kind of distance unit. So my amplitude describes my height, and I can have two waves that have the same amplitude and different periods. Now, let's take a quick look at this one. If I want to, say, start at this point, and I want to find where the period is, or where one period is. Effectively, I go from 0 to 0, but I'm going up here and I'm going down here. Is this a period because I'm going up and up? No. I've got to be at the same type of place on the wave. So there would be one period. Just so we're clear, what I need to be able to do is basically cut and paste this wave over and over again in order for it to truly be one period. So period is the time it takes for one cycle. And everything I've drawn here is symmetrical except this one. So we can talk about oscillations, we can talk about periodic motion. It can still have a funky shape as long as it is happening exactly the same thing over and over and over again. So that's fun, that's useful, but it's not specifically what we want to spend most of our time on. Oh, there is one more term to consider, and that's called the phase constant. We're not going to spend a lot of time on it, but the phase constant would be a shift left and right. So I draw a wave like so. These two waves have the same period. That length is still the same from one point in the cycle to the next. That means they have the same frequency. They have the same amplitude. The only difference is that they are offset. So I would say that this distance I represent with the Greek letter phi. This is a phase constant. And again, that's not something I want to spend a whole lot of time on, but I just want you to kind of be aware of. So what we really want to focus on now in Physics 2 is not just an oscillation, but specifically we want to talk about something called simple harmonic motion. And we'll abbreviate that for the rest of the course as SHM. But the idea behind simple harmonic motion is that not only is it periodic, but it is smooth. It's a sinusoidal oscillation. In other words, it's one that can be represented by a sine wave or a cosine wave. So let's look at an example of something that may not appear immediately to be sinusoidal. Let's look at a mass on a spring. So to start with, we're going to take our mass on a spring and we're going to stretch it out. So this will be our mass. And as we stretch out our mass, what's going to happen as soon as we let go? This mass is going to swing back, right? So we're going to end up with our mass moving through. And remember, if we're truly talking about an oscillation, there's an equilibrium position. So the point where, under normal circumstances, if I were to just start right here, the mass would be happy and it would just sit. But because I've developed some momentum, I have some velocity. So again, my point of I'm going to have the most acceleration here because I have the most force out here. I have the most spring force. And as I move through, I get to a point where I have no spring force, but I have my momentum carrying me through. And now I compress my spring. And when I compress my spring, I increase the spring force. And then I get to a point where the spring is going to push that mass back. So basically what I have is this back and forth motion of the mass on the spring. So we're going to do kind of the same thing we did with the pendulum. So in this case, again, we're going to call this our equilibrium position. So in other words, we're going to say x equals 0 here. This is where we're at 0. Here, I'm going to say this is my maximum position. And here we can, and remember we said that our maximum position from equilibrium is actually the amplitude. So that's how I'm going to choose to represent that. Well, here, and we'll say that's x. It's literally a distance from equilibrium. So down here, again, x is equal to this same amplitude, but it's just in the opposite direction. Okay. So what about velocity? Well, we said that here our initial velocity starts at 0. But I have a maximum acceleration here. So I have a maximum acceleration because my force is at a maximum. And just to be clear, this isn't like mass times acceleration times x. This is like maximum, the word. Okay. Here, my velocity is the greatest, as I've had a chance to accelerate the most. So my velocity picks up, and at this point, my velocity is at a maximum. But my acceleration is at 0, because this is an equilibrium position. In other words, force is 0, so acceleration is 0. And then when I get down here, my velocity is, again, 0. And my acceleration is a maximum, but in the opposite direction. So it's a maximum, but now my acceleration is this way, whereas up here my acceleration was this way. So we know, just empirically speaking, that this is how a mass on a spring behaves. That's why I'm bothering to go through this, just so we can talk through how we already know this works. But now let's look at this graphically. Now, there's three things we're going to look at. We're going to look at position, we're going to look at velocity, and we're going to look at acceleration. And the other cool thing about these three is we know from Physics 1 that the position with respect to time, so as I change position with respect to time, that's velocity. So remember that velocity is change in x with respect to change in time. We can call that the slope of position. And I know you haven't had, I know calculus is not required for this course, but if you've had calculus, there's actually a really pretty explanation for simple harmonic motion. And I want you to see that I'm not just pulling this out of the air. I want you to see where this comes from. So effectively what we're looking at is the derivative of x with respect to time. And if you haven't had calculus, don't freak out. I don't expect you to derive any of this on your own. But it's just important, again, for you to see that simple harmonic motion is not just some magical thing that we said poof and there it is. It actually has a really straightforward explanation. So we know that this is how we define velocity. We also know that we define acceleration as change in velocity with respect to time. In other words, it's the slope of velocity with respect to time. When we start talking about that in terms of calculus, again, that's the derivative of velocity with respect to time. But because we know that this is equal to velocity, in calculus we can also say that d squared v over dt squared, in other words, we're looking at the second derivative of, that would be not velocity. We're looking at the second derivative of position with respect to time. Okay, so if we take this derivative of position once, we get velocity. If we take it a second time, if we take the derivative of velocity with respect to time, we get acceleration. Okay, so this is where it actually starts to get interesting. So let's play graphically with our mass on a spring. Let's do it, we'll do it this way. So the first thing we're going to look at is position with respect to time. And in my initial case, my position is at a maximum, and we're calling that maximum A. We also know that initially, we can talk about velocity with respect to time, and initially my velocity is 0. We can talk again about my acceleration with respect to time. So initially my acceleration is in this negative direction. If we call this a positive x, acceleration with a decreasing position, we're looking at a negative acceleration. So I'm going to call that negative A max. Okay, so that's my first case. Then as time goes on and I hit this equilibrium position, I know that my position, that equilibrium position, we say is 0. But the velocity at that point is at a maximum. And actually, to be more correct, the velocity is moving in a negative direction. So we'll say we're at negative Vmax here. And my acceleration at equilibrium is 0. Okay, then down to our third case, we've scrunched up, and so now we're at a negative position. My velocity is back to 0, and my acceleration is now in the positive direction. And then we start to repeat the process. Now we go back out. So we go here, and then it doesn't take a whole lot of imagination to see we're just going to work our way back up. So we get back to our maximum amplitude. And just so we're clear, this is negative amplitude here. And then we hit the middle point in this case, where we have a positive maximum velocity as we're moving back through this way. And then we slow down and come to a stop as we get back up here. And then with acceleration, so this is where we are here with the maximum acceleration this way. And then as our force drops off, our acceleration drops off. But then our momentum pushes us through. And so we actually begin to accelerate in the other direction. And so we're back to negative A maximum. So I'm going to call this particular point A max right here. So again, this is what we know just from the way we know a spring behaves. Now, here's the kicker. Here's where this actually gets interesting. So how do I connect the dots? That's my question to you. How do I connect these dots? Am I going to connect them just straight zigzag lines? Am I going to have this triangular function? Is it going to be a square wave of sorts? How do I connect these dots? Well, we could do this one of a few ways. We could just take a bajillion-T actual measurements, and enough measurements will give us a nice smooth line. Or we can use our math, and we can use a little bit of differential equations, which, again, I don't expect you to know, but I do want to show you how this works.